Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus. In this lecture we're going to be looking in greater depth to the idea of signed area. First of all of triangles and then of more general quadrilaterals and n-gons. Along the way we're going to introduce an important notion from linear algebra, somewhat modified, called the cross product. That'll be a little bit novel actually. And we're also going to touch base with a classical formula from the 18th century, going back to Meister. Okay, so the starting point is the definition which we introduced at the end of the last lecture, where we defined the area, actually the signed area, of an oriented triangle of a rather particular kind. A triangle of the form OAB, where O is the origin. And so here the point A is, say, the point AB, and the point B is CD. So there's our oriented triangle OAB. And we defined the signed area of this oriented triangle by the following crucial formula. All right, that S of OAB is 1/2 of AD minus BC. AD minus BC. And we denoted that signed area by a little s, which naturally kind of goes with the idea of signed area. And it's actually also in line with the German s, which originally motivated Leibniz's introduction of the integral symbol. Okay, this quantity AD minus BC is very important in mathematics, and I hope that you all know that the determinant of a 2x2 matrix is exactly AD minus BC. So here's a 2x2 array of numbers, a matrix, A, B, C, D, and this is an important concept from linear algebra, and such a matrix has associated to it a single number which somehow captures some essential properties of it, called the determinant, and that determinant is the A times D minus B times C. We've also seen this notion in the context of the two-proportion theorem, when we were talking about when two proportions were equal. I remind you that if you have a proportion A to B and another proportion C to D, then they are equal precisely when AD minus BC equals 0. That actually has a direct implication to the meaning of this signed area. It's telling us that if we think about the vectors emanating from the origin to the points A and B, so this will be the vector AB, and this will be the vector CD, then those vectors are parallel or in the same direction when they're a multiple of each other. And that's exactly the same kind of relation as the one here, giving equality of two proportions. And so this signed area is capturing, in some sense, the non-parallelism of these two vectors. If the vectors are parallel, then AD minus BC is going to be 0, and that signed area is going to be 0. So that's another connection with linear algebra. All right, so this is a very important notion, but currently we only have defined the area in terms of this oriented triangle of a rather particular kind where one of the points is the origin. Now it's going to be a sort of a theme for us that the notion of area is something that we have to build up level by level, step by step. So we're not allowed to assume that we just have a intuitive notion of area. We're obliged to define area, and we're going to do that in a step-by-step fashion. Okay? That's a rather important understanding and appreciation to have, that we're building up the notion of signed area here. So now I want to introduce a notion into planar affine geometry, which is going to really help us in understanding the idea of signed area. And it's coming from three-dimensional linear algebra. It's called the cross product. But this is not the cross product that you may be familiar with if you've taken linear algebra or engineering courses. It's not the product of a vector in space with another vector in space giving you another vector in space perpendicular to the two of them. Okay, that's also called a cross product. The cross product here is more limited and only concerns vectors that are in the plane. Okay, so here's the definition. If u is the vector AB and v is the vector CD, so these are planar vectors, vectors with two components, then their cross product, u cross v, is by definition AD minus BC. AD minus BC. So here, the cross product of two vectors in the plane is a number. Okay, that's an important distinction with more standard terminology. But it'll be really useful for us to have this notion under our belt, as you'll see. Okay, so this cross product is relatively simple, but it has some crucial properties that are going to be very important. And first of all, it is basically a linear kind of situation. The cross product is linear. And what does that mean? Well, here's precisely what we mean by that. That if we take the cross product of u with the sum v plus w, I remind you that vectors can be added. So u cross v plus w is the cross product u cross v plus the cross product u cross w. So I'm not going to put brackets here. I possibly could put brackets here and here to clarify that this is a number and this is a number, and here we're adding two numbers. Okay, but the convention is that this cross product takes precedence over this addition. All right, so this means take the cross product of u and v, take the cross product of u and w, and add them. And similarly, if we interchange the order, u plus v, say, cross w, then there's a distributive property in this direction as well. So this is the same as u cross w plus v cross w. And the other linear aspect is what happens when you multiply one of these vectors by a scalar. In other words, a number, lambda, which for us typically always means rational number. So lambda is a rational number. Then if you take the vector u and you multiply it by lambda and then take the cross product of that with, say, v, you end up getting the same thing as lambda times the cross product of u and v. And that's also the same as u cross lambda times v. So this scalar can be put in front of the u, or in front of the v, or in front of the entire cross product. They're all three equal to each other. So these three properties, we'll refer to them as the linear properties of the cross product. And it's a good exercise for you to check that these are actually true. Another very important property of the cross product is that it's skew-symmetric. And this tells us what happens when we interchange the order of the two vectors. So u cross v and v cross u, how are they related? The answer is by a minus sign. U cross v is minus v cross u. So we interchange the order, we introduce a minus sign into the cross product. That has a consequence which is worth noting, that if u and v are the same, say u cross u, then we have to get 0 as the cross product. Because whatever number that would be, it would have to be equal to negative of itself, and there's only one number that's equal to negative of itself, and that's 0. So the cross product between two planar vectors is a number, it has a bunch of linear properties, and it's crucially skew-symmetric. It'll be a useful tool for us to work with and introduce and calculate signed areas of all kinds of things. Now it's pretty clear that there's a strong connection between cross products and signed areas. So let's just clarify that. Here's our triangle again that we've been considering, triangle OAB, and it's oriented, denoted by that little circle there with the arrow, meaning that we should go in this direction. Okay, and we've said that the signed area of OAB is equal to 1/2 AD minus BC. And now we can just observe that that's actually just 1/2 of a cross product. Because this vector here, the vector OA, let's call it U, is just AB. And this vector here, let's call it V, is the vector CD. And we've just defined the cross product of U and V to be AD minus BC. So this signed area of this oriented triangle is equal to the cross product of this vector with this vector. So if we just express it in terms of the points themselves, the signed area of the oriented triangle OAB is 1/2 of OA cross OB. So a natural question is, could we use this to define the signed area of a more general oriented triangle, say ABC? ABC somewhere in the plane, not necessarily connected to the origin. And the answer is happily yes. Now, in order to get at the signed area of a general triangle, we need a preliminary fact first. That's given by this triangle cross product theorem, which says that for any oriented triangle ABC, say like this one here, is an oriented triangle ABC. You can see that the orientation is specified by this circle inside with the arrow, meaning that we're going in this direction. There's a circular aspect to these three things. Even though we write it ABC, it's really the order, cyclical order that matters, the order that going in this direction as opposed to going the other direction. Okay, so for any oriented triangle such as that, ABC, the following three cross products are all equal. AB cross AC equals BC cross BA equals CA cross CB. How can you remember that? So think about the cyclic ordering here. All right, the first cross product is AB times AC. So we're starting at a vertex, and the first vector that we're considering is the one that goes from that vertex to the next vertex. And then the other one is the one that goes from the first vertex to the one following the next one. So start at A, then we get AB first, and then AC second. Now if we rotate by 1 and go to B as the starting point, we're still going in that direction, then the first vector is BC, and then the second vector will be BA. So we have BC cross BA. And if we go to the third point, C, then the first vector, if we're still going in that same order, would be CA and then CB. Okay. So there's nothing really confusing about this, as long as you remember that there's a cyclical ordering here. We're going from here to here to here. So it's the relative cyclical order that's crucial. Okay, so let's prove this. We're going to prove it by setting up some vectors and using the vector linear algebraic properties of the cross product. So let's set the vector AB to be U. Let's call that U. And the vector AC will be V. Then the third vector that we're going to be using is the vector, say, BC, going from B to C. And that's going to be V minus U. Let's just check to make sure that we believe that. So this is V minus U. You can see that if you start here and you take U and then you add V minus U, that combination is same as just V. That's why this vector is V minus U. So when you add it to U, you just get V. Another way of remembering this is that to go from the head of one vector to the head of another vector, as in BC, you take the difference of the final vector minus the initial vector. Okay, so now let's have a look at BC cross BA. In terms of U and V, what are these things? Well, BC we've said is V minus U. And what is BA? Well, AB is the vector U, so BA will be the vector minus U. All right, now by the distributive property of the cross product, this is going to be V cross minus U plus minus U cross minus U. And I've sort of taken both of those minus signs out. So there's a minus U cross minus U actually here, but the minus sign comes out front and then the other minus sign comes out front. They both multiply to give us just a plus sign. All right. So we get V cross minus U plus U cross U. But this minus sign can come out front by the linear property. So we get minus V cross U. And the U cross U is 0. That's the skew-symmetric property of the cross product. Now, minus v cross u is the same as u cross v. That's, again, the skew-symmetric property. And by that time, we see that we're back to AB cross AC. So we've been able to manipulate things to convince ourselves that BC cross BA is indeed the same as AB cross AC. And now let's check the same thing for this third cross product, CA cross CB. What is CA? CA. Well, that's going to be minus V. And what is CB? Well, it's the negative of BC, so it's going to be U minus V. All right, from C to B is going to be the negative of this one, U minus V. And then the linear property of the cross product, again, gives us this is minus V cross U, that's the first term. And then there will be plus minus V cross minus V. And for the similar reason as up here, the two minus signs combine to give us a plus sign. And in any case, this thing is 0. And so the next line is just minus V cross U, or again, the minus sign has been taken out by the linear property. Again, minus V cross U is the same as U cross V, and we see that we're back to AB cross AC. So yes, indeed, each of these other cross products are the same as the original one. So let's have a look on the diagram. What is this actually telling us? Well, it's telling us that AB cross AC is the same as BC cross BA is the same as CA cross CB. In each case, the first vector is in the direction of the next one in the order, and the second vector is the vector in the direction of the previous one in the order. So it's nicely cyclically symmetric. And that's really great. That means that when we have a triangle like this, if we want to compute one of the cross products, we can replace it with any of the other two cross products as long as we go in the cyclical orientation that the orientation dictates. So it gives us a flexibility in terms of defining and calculating cross products. All right, great. So now here is sort of the main definition. For an oriented triangle ABC, its signed area is S of ABC equals 1/2 AB cross AC. But it also equals 1/2 BC cross BA. It also equals 1/2 CA cross CB. We've just seen in the previous theorem that all of these quantities are the same. So their common value is going to be the signed area of the oriented triangle. So we don't insist that we have to choose one particular vertex because we really want to think of these three vertices as all being sort of on an equal basis. So it's 1/2 of AB cross AC, or it's 1/2 of BC cross BA, or 1/2 of CA cross CB. So for example, here is a oriented triangle ABC. A is the point 3, 1, B is the point 4, 3, C is the point 1, 2. Then the signed area of ABC is what? Well, we can use any one of these three to make the calculation. The previous theorem tells us we're going to get the same answer whichever one we use. So let's use the first one, say AB cross AC. AB cross AC. We have to find those two vectors, which are relative positions, and then take their cross product. So what's the vector AB? Well, it's going to be the difference in the coordinates here. So final minus initial. 4 minus 3 is 1. 3 minus 1 is 2. So this is the vector AB. It's the vector 1, 2. And what about the vector AC? Well, again, final minus initial. 1 minus 3 is minus 2. 2 minus 1 is 1. So there's the vector AC. So this is AB cross AC, and we have to take 1/2 of that. And what is the cross product? Well, it's an AD minus BC kind of thing. So we have 1/2 of 1 times 1 minus 2 times minus 2 for a grand total of 5/2. And I'll let you check that you get the same number if you start with the vertex B or the vertex C also, and consider just the vectors emanating from either of those. This is great. So now we have a definition of the signed area of an arbitrary oriented triangle.